Now let us talk about an important term in any system, which is efficiency. So in any system, some of the energy is lost when producing electricity from some other energy form. For example, you have a solar power plant. Then all of this light which is incident on solar panels cannot be converted into electricity. Some of it is lost in a variety of ways, in variety of forms, and the lost energy is normally converted into some form which is other than electricity. So obviously in this case the output energy is always less than the input energy, and if we take the ratio of output energy to input energy, then this is called the energy efficiency, or simply efficiency, and normally it is expressed in percentage given by this formula, where efficiency in percentage is equal to output energy divided by input energy into 100%. Moreover, because power is the rate of flow of energy, therefore efficiency can also be represented in terms of power simply by substituting the power instead of energy. So efficiency for can be calculated based on powers by taking this ratio, which is output power divided by input power, and you multiply it with 100 to take it into percentage. Let us take a look at one of examples. So a mechanical energy is supplied to a DC generator at the rate of 4200 joules per second. So the mechanical energy which is provided by the prime mover to this generator is 4200 joules per second. So mechanical energy is 4200 joules per second, which is provided to this provided to this DC generator. So obviously 4200 joules of energy is provided every second. So this is actually power, the power which is at the input of the generator, which is supplied to the generator. The generator delivers a 32.2 ampere current at 120 volts. So the generator terminal voltage is 120 volts and it is capable of providing 32.2 amperes of DC current. So overall this generator can deliver an output of 120 into 10 into 32.2 watts. So what you are required to do is to calculate you are required to calculate the percentage efficiency of the generator, and you are required to tell how much energy is lost per minute of operation. So let us take a look at the solution. So first of all, the input power is given by 4200 joules per second, because 4200 joules of energy is reaching this generator every second from the prime mover. So 4200 watts of power is input at the generator, and the generator produces an output power of 32.2 into 120 watts, which is 3864 watts. So the efficiency of this generator is in output power divided by input power into 100%. That comes out to be 92%. Now moving on to the second portion, how much energy is lost per minute of operation. Remember that this is the energy, this power in watts is a energy supplied per second of operation. You are required to tell how much energy is lost per minute of operation. So if you calculate how much power is lost, which is input power minus output power, so 336 watts of power is lost, or 336 joules for each second are lost. So in 1 minute 336 into 60 joules will be lost, which is 20.16 kilojoules. So 20.16 kilojoules of energy will be lost per minute of operation of this particular generator. Let us look at an exercise to solidify the concepts in the previous example. So you are required to express the energy lost per minute of operation in example 1.1 in kilowatt hours, kilocals and BTU. So the energy lost per minute of operation in example 1.1 must be converted into kilowatt hours, kilocals and BTU. The catch over here is that you have to show all the calculations starting from lost energy per minute of 20.16 kilojoules. So as we saw previously that 20.16 kilojoules of energy is lost per minute of operation. So starting from this, you have to convert this 20.16 kilojoules to kilowatt hours, to kilocals, and to BTU. And you cannot use the conversions which we have derived from the previous, like you cannot use like 3412 BTUs are equal to so many joules, so many kilowatt hours. So you cannot use those conversions which we have already derived. You have to derive from this 20.16 kilojoule, and you have to move to first of all kilowatt hours, and then you have to move from 20.16 kilojoules to kilocals by using the appropriate concepts. So this exercise will solidify your concepts about the energy and the relation between units and how to derive the relation between different units. So what you have to do is, आप लोगों ने 20.16 किलो जाउल से स्टार्ट करना है और इसको कन्वर्ट करना है अपने किलोवाट आवर में. इसको करने के लिए आपको ये अपने ध्यान में लेके आना है कि 1 जाउल इज इक्वल टू 1 वॉट सेकंड के बराबर होता है. तो उधर से आपने लेके चलना है और फिर इसको किलोवाट आवर्स तक लेके जाना है. इसी तरह से किलो कैल्स में जब आपने जाना है तो आपको पता है कि इतने जाउल्स जो हैं वो इतनी कैलोरीज के बराबर होते हैं, या एक कैलोरी में 4.18 जाउल्स होते हैं. तो उस कन्वर्जन को आप यूज कर सकते हैं, क्योंकि आपने वो वाली कन्वर्जन कहीं से हमने ड्राइव नहीं की थी, वो हमने एज इट इज एक्सपेरिमेंटल स्टडीज से फाइंड आउट की थी. सो उस कन्वर्जन को आप यूज कर सकते हैं, लेकिन जो चीज हमने ड्राइव की हुई है वो आपने एज इट इज उसका एंड रिजल्ट नहीं यूज कर लेना, आपने ये डिराइव करके दिखाना है. So this is your exercise, and you have to solve it in your own capacity. This is not an assignment, but as I have as is my way, I normally give exercise questions in the assignments. So if you have already solved it, you will have no problem in submitting the assignments later on. Now let us talk about calorific values of fuels. And what is this? So amount of heat produced by complete combustion of unit weight of fuel is known as its calorific value. So the amount of heat produced, which will obviously be in kilocals, by complete combustion of unit weight. So if you by unit weight, I mean that if you have coal, if you have 1 kg coal, that is 1 unit weight of coal. So the energy amount of heat produced by that 1 kg of coal is called the calorific value of that coal. So the calorific value is expressed in, for example, for solid and liquid fuels, it is represented in kilocals per kg, and for gaseous fuels it is represented in kilocals per meter cube. So how much cubic meters of gas need to be burned to produce how much kilocals of heat energy. So that is what this calorific value tells you. So greater the calorific value of fuel, higher is the amount of heat produced, and that fuel is considered to be of good quality. So a fuel with low calorific value can also be combusted to produce electricity, but that will produce a lot of pollution, and because that will be a low quality fuel. This table represents the calorific values of various types of fuels. For example, we have different forms of coals, which is lignite, bituminous coal, and anthracite coal. And straight by looking at the calorific value, we can tell that anthracite coal is of the highest quality, as it has the highest calorific value, which is it can produce 8500 kilocalories of heat energy for every 1 kilogram of fuel burned. And the lignite is the lowest quality coal which you can burn, which has 5000 kilocalories per kg. So straight by looking at these calorific values, you can tell that if you have anthracite coal, you need to burn around about 2/3 of that coal, 2/3 of a kilogram, and to produce the same energy, you have to burn a whole kilogram of lignite. So like this is a comparison which you can make from take from the ratios of these calorific values. So liquid fuels, we have heavy oil, we have diesel oil, and we have petrol. So all of these have approximately similar calorific values, but calorific value of petrol is greater than calorific value of diesel oil, and petrol will result in lower pollution as compared to diesel oil. Then we have gaseous fuel, which for which we have natural gas, and then we have coal gas. So natural gas has a calorific value of 520, but coal gas has a calorific value of 7600. So coal gas is the obviously the better candidate and a high quality fuel.